We present Dream Lift Animate, from single images to animatable Gaussian avatars. The goal is to democratize personalized avatar generation. Instead of capturing a human in an expensive and time-consuming way in a capture studio, we want to enable animatable avatars from a single input image, because this single input image can be captured from consumer devices like smartphones, which are widespread, lightweight, and vastly available. This problem exhibits difficult challenges because the sparse inputs only describe a part of what we want to reconstruct, so we need to hallucinate novel views in a plausible and detailed manner. Also, the lifting from 2D to 3D is an ambiguous problem. Finally, most related works completely ignore pose-dependent effects and only model view-dependent effects with spherical harmonics. In this work, we enable more complex pose and view-dependent effects. Related work can be divided into three categories. On the left-hand side, we have animatable avatars, which are often represented as MLPs, for example, as implicit functions or signed distance functions. These can be rigged with a body model, but are often of lower quality or only animatable as a texture mesh. On the right side, we have Gaussian avatars that are static. They're often generated with diffusion models and have a lot of details. However, since they're not animatable, we need to rig them. In the middle, we have readily animatable Gaussian avatars. The most closely related work is Idle from CVPR 25. Idle takes a single input image and maps it to an animatable Gaussian avatar in the UV space. As a difference to ours, they only input a single image. They do not explicitly synthesize null views. This leads to artifacts in the unobserved regions, like a top of the head, side views, or back views. In ours, we first hallucinate null views and then render an animatable avatar. In addition, our avatars also model pose-dependent effects. Here's an overview of the pipeline. Our work first conducts a dream step, where we hallucinate null views of the input image with a video diffusion model. In the lift step, we map this novel views to a pose-based reconstruction. This pose-based reconstruction has a Gaussian point cloud, which can be then mapped to a UV space latent, and then this latent can be turned into a Gaussian parameter map in the Animate stage. This map can be deformed and rendered. Here's an overview of the entire pipeline in more detail. We're going to go through each step in more detail. In the dream stage, we have two different modes. During training, we use scans from a data set, we render them from novel views, and we just inject those ground truth views directly. In the inference stage, we synthesize novel views with a video diffusion model called Animate. In the second step, the lift step, we first perform a pose-based reconstruction. We feed pluck arrays and the 4 input views to a large Gaussian reconstruction model. This leads to a pose-based Gaussian reconstruction, which can already be splatted and supervised. However, this reconstruction is not animatable. So we use the features from the pose-based reconstruction model G, and we filter Gaussians with low opacity. We compress this representation with farthest point sampling and cross attention. The output is a very compact representation of the input. So this latent representation is encoded and then queried with the vertex position maps given the target pose. The output of this encoder is an avatar latent code, which describes this avatar in the UV space. Now we transition to the Animate phase. In Animate, we take the avatar latent and the semantic map, and then we upscale it to a canonical Gaussian map. This has been done in similar ways in other works. However, the canonical Gaussian map cannot deform or cannot apply pose-dependent effects, so we have to condition on surface normals and a relative vertex position map. This gives the model information about the target pose. In addition, we condition on pluck arrays, which describe the camera position and view direction for the target view. This produces a Gaussian offset map, which can be added to the canonical map. Together, this yields a Gaussian parameter map that can be sampled, deformed with simple X, and splatted to an image. Now that we have discussed the pipeline overall, let's talk about training. Our Gaussian parameter decoder is trained with an L1 loss and a VGG loss and a mask supervision. To enable more details, we use a patch discriminator and we regularize the latent with a KL loss, and we also apply an L2 regularization on the latent code for the Gaussians. In addition, we supervise the unstructured post-based reconstruction with VGG and the mask loss. Training is very fast. We train for 10 epochs at low resolution, 10 epochs at high resolution, which together takes less than a day. For evaluation, we compute metrics on actors HQ and 4D dress, and we show qualitative results on SHHQ in the wild images. Note how idle the best performing related work struggles with the face, especially the head region, because hair turns out to be white because it's not visible in the input, and side views tend to exhibit artifacts. This is even more notable on 4D dress. So here, if you pay attention on the bottom right example, you can see the artifacts on the shirt and on the head. Now let's see some in the wild examples on SHHQ. This input image is extremely challenging because the face is mostly occluded, the head is hidden in the pocket, and the jeans and jacket exhibit a lot of wrinkles. Still, our method is able to reconstruct an animatable avatar that can be rendered from novel views with realistic wrinkles. On the bottom, we have an example where the person touches their hips. In the middle, we have two examples with a mini skirt, and on the right, two more examples. Here are 6 more examples from the SHHQ dataset. Each image is reconstructed and animated with the same sequence. Our design enables post-dependent effects. Post-dependent effects can be enabled by conditioning the Gaussian parameter decoder on normals and on the relative vertex position map. This means that the Gaussian parameter map is aware of the target pose. Here you can see the pose-dependent effects. This is particularly notable on shoulders and elbows. Most related works, they model Gaussians with view-dependent effects by using spherical harmonics. In our work, we model this with a more expressive way by conditioning the Gaussian parameter decoder on pluck arrays. Pluck arrays describe the camera position and orientation. So we have an expressive way of adding view-dependent effects. This means that the Gaussian can focus on producing high-quality views from the target pose. The latent space also enables editing. The structured avatar latent code follows the UV layout, seen on the top right. For example, if you pay attention to the face in the bottom left, and we overlay a latent code, you can see the face even in the latent space. This enables editing like face swapping, or also virtual try-on. Let's take 2 reconstructed subjects and replace the subject on the left, the face, with a new face. Similarly, we can take the shoes and just replace the shoes. Finally, we observe some emergent capabilities that usually only show up with generative models. The structured avatar latent code represents an avatar before deformation and before view-dependent effects. If we now interpolate the structured latent code, we can morph between one subject to another. In summary, we present Dream, Lift, Animate, from single images to animatable Gaussian avatars. Our core idea is to decompose the reconstruction into 3 steps. In Dream, we synthesize novel views. In Lift, we perform post-based reconstruction and map those reconstructed Gaussians into a latent space. And in Animate, we take this latent space and turn it into post and view-dependent Gaussians that can be rasterized. Thank you for listening.